So first, the short surface gravity. You can hear some sketches of how this wave looks like. Okay? The short gravity. So for example, what you can have a look at is water parcels. How do they move under a short wave? And this is shown here just next to my head. You can see the trajectory, the movement pattern of a water parcel. Okay, and you can see near the surface, it just goes back and forth and up and down. Okay? And as you move downward, the radius of these motions becomes smaller and smaller, which means that the speed becomes much smaller. And this one is the particle speed, not the phase speed. And then the wave disappears at some depth. Okay, so these waves don't reach the seafloor. They propagate in space, and that one example are just wind-generated surface waves in the deep ocean. Okay, there are short waves. And that's one feature. They don't touch the seafloor. You can show using mathematics and the fundamental physical conservation equations for these waves to work out the dispersion relation. Okay, so the ratio of wavelength over wave period is the phase speed, and you can show that the phase speed of these waves only depends on the wavelength. Okay, g is acceleration due to gravity, as you know. 2 pi, you probably can work out what pi stands for, and it's only the wavelength that determines the speed. The longer the wave, the faster it propagates. Okay? The longer the wave, the faster it propagates. So if you have a storm over the Southern Ocean, you can actually tell about where the storm center is, because the fastest, the longest waves actually appear first at your observation station. Okay? So there are methods by which you can identify the storm center just looking at the wavelength of waves, or the phase speed of waves as they arrive at some distant location. This is what we call short surface gravity.